Okay. Uh, Good evening, everyone. Today I'll be discussing the contents of week 12, followed by few questions pertaining to that week. Um, okay. So in this week is more of practical applications, how to measure the kinematics, how to analyze it, what kind of machinery can be used to measure the movements, and a little bit of introduction into gate cycle. Okay. So last week we saw that there are three different ways to uh, parameterize the rotations. Those were rotation matrices, Euler angles, and quaternions. Okay. One of the problems that is present while using Euler angles is the problem of gimbal lock or singularity. These might not mean the same thing, but gimbal lock is more of a phenomenon, whereas singularity is studied in very in different aspects. By but in the subsequent slides or in this particular course, these two are used interchangeably. The problem that is present in case of angles is that if the middle, so this is the middlemost middle ring. If these three rings were to rotate in different ways so that they uh, represent the axis that the object will be present in the Cartesian coordinate system, this is the inner one and this is the outer one. In an event where the where the ring that is representing the where the middle ring is at an angle of 90 degree, at an angle of pi by 2 with the other rings, uh, so essentially what this results in is in that these two other rings are uh, cohesively present in one plane. So the number of degrees of freedom that you have decreases. So now the solutions that you would get is no longer dependent on all the three axes. Rather, it is dependent on the angle between what between the change in orientation along this axis and along this axis. So that is one of the problems that Euler angles had. So each of the methods that we saw had their own problems. Rotation matrices are kind of complicated. Uh, we'll see the we'll see details of that in a later slide. Or Euler angles have the problem of gimbal lock, and quaternions are kind of difficult to uh, intuitively understand because they lie in a 4D hypersphere. They have uh, one real part and three imaginary parts. So because of such a where one of the angles is, this will be, if theta is the angle, I think so. I might be wrong. But because of such a coordinate system, it's kind of difficult to visualize it and intuitively understand. But however, there are certain tools that can be used to kind of visualize how they look like, not completely, but you get a feel of what the system would look like. Anyways, so these were some of the problems. So depending on what your need is, you need to decide which parameterization method you will choose. Coming to some of the more details, so as I said, rotation matrices is slightly complex because it has a lot of terms. So to represent any 3D orientation in terms of rotation matrices, you need 9 values. It's a matrix like right like this. um, and in case of quarter ants, you need 4. In case of Euler angles, you need 3. Ha, the in if you were to look at the continuity in measurement, rotation matrices are smooth and continuous because for each of the orientations there will be a individual rotation matrix. Quaternions are also kind of uh, continuous except for something known as antipodal symmetry. So what this means is that uh, the solutions are such that for along the center, if suppose it's, I know it's a 4D hypersphere, but if this was a circle, along this center, if there is one solution here, there will be one more solution on the opposite side in at an angle of 180 degrees. This is what antipodal symmetry means. Except for these conditions where there will be a discontinuity in measurements, for other points in the hypersphere, the measurements are kind of continuous. In case of Euler angles, the singularity Gimbal log problems arise, where uh, if the angle of the middle ring is 90 degree, you lose out on degrees of freedom. Okay. Uh, so, uh, in case of rotation matrices, you need to know the sequence of selection, whether it's XYZ, XZX, what is the sequence. That is not the case for quaternions, but for Euler angles also you need to know the sequence of selection, because the Euler D uh, code that you give your MATLAB workspace to compute the Euler angles requires the sequence of the axes. In any of these three matrices, the interpolation is kind of a problem. Uh, However, for with uh, in terms of quaternions, there is an algorithm called as slurp, which if you put in the quaternion values, it will give you an interpolation of how the movement is. And again, uh, averaging is not straightforward in case of rotation matrices and Euler angles. Now, for quaternions, there is something known as Markle's algorithm, which lets you calculate the average by taking the highest eigenvalue for all the eigenvectors that you have. So you get an average of sorts in case of quaternions, whereas you don't get it for the other methods. In case of the in terms of the measurement angle, it's both quaternions and rotation matrices are suitable for measuring the whole 360-degree movement. In case of Euler angles, this problem again comes because of the singularity, where you lose out on degrees of freedom. But in case of Euler angles, your measurement range decreases. There are certain points that the Euler angles cannot, for which Euler angles can be computed. They can be computed, they might not mean much. Okay. Again, with for quaternions, there has been some algorithm, some of the algorithms developed to linearize the values, whereas the rotation matrices and Euler angles are not that straightforward for linearization. So it seems like quaternions are kind of, everything is figured out for quaternions. The only problem is the visualization, but there are tools that can be used to visualize it. Okay. Now let's look at a that. So in one of the previous classes, we saw different methods of measuring hand kinematics. There was data glove, there was electromagnetic sensors, there was also inertial movement unit or IMU. So these IMUs are chips, kind of like chips that you can place on the segment that you want to observe the kinematics for, and then you can record their movement, and you get your and you can do your further analysis. In this particular case, uh, the they have successfully designed a IMU based hand kinematic system uh, for their uh, hand kinematic system, because they are interested in hand kinematics. So the measurements are done such that there are chips present on the uh, distal phalanx, on the middle phalanx, if you were to see a finger, on the proximal phalanx, and on the wrist. And essentially these chips give out the measurements in terms of quaternions. So you can conjugate the wrist, uh, you can conjugate the quaternions that you get from, you can multiply the quaternions conjugate that you get from the wrist to the proximal one to get the angle that you would see in the metacarpophalangeal joint. So MCP is metacarpophalangeal joint, PIP is proximal interphalangeal joint, DIP is distal interphalangeal joint. Similarly, you can compute the uh, quaternions. You can compute the relative angle from the at the PIP by using a conjugate of Q proximal by multiplying a conjugate of q proximal with the q mid. So essentially this conjugate of this multiplied with this. Similarly, you can also compute q dip, and these you can then convert to Euler angle using the Euler d form command, or you can write some of your own algorithm, and you get your Euler angles, which you can further use to uh, visualize stuff in 3D. Okay, so you track these values, these four chips in real time. You get your angles, and that's how you can sort of design what is the uh, what kind of movement the hand goes through, what is for a particular posture, what are the angles that the hand needs to move at to make that posture. And in case of any pathological problems, if there is a change in these angles, uh, if there is a change in the movement of the hand, these angles will change, and you can sort of calibrate the results according to each pathology. Okay. Okay. So coming to the measurement system that they have used, in so they have used different IMUs at different points in the hand. So you saw DIP, sorry, DIP. So this is the if you are looking at a single finger, this is a sorry single figure. This is how it would look like, right? To compute everything properly, they have used multiple sensors. Uh, since if you were to see this movement, there is only 1 degree of rotation here. There is no, it can't be moved in the, if this is the x direction, it can't be moved in the y direction. So, for the distal phalange sensor, they have used sensor, and the middle phalange sensor, they have used sensors which have 1 degree of freedom. For 5, 8, 11, and 14, which are at proximal phalange, they have used sensors which have 2 degrees of freedom. The thumb, the carpometacarpal sensor for thumb, has 3 degrees of freedom because thumb also allows for rotation. And there is a reference wrist sensor because it shouldn't ideally move when these movements are occurring. Okay. So the chip itself for the IMU is a BNO 055 chip, which has a acceleration sensor, a gyroscope, a magnetometer, a 32-bit microcontroller. So it can convert using sensor fusion algorithm. It can take measurements in terms of cotton ions and then relay the information. It's kind of on the smaller side, 3.8 into 5.2 square, so tiny. The motion, once the if the chip is placed on some finger, the usual motion will give an idea of the quaternions, the linear acceleration, the rotation, gravity, and it is kind of robust. Okay. So, in any case, you if you are developing any new method of measuring something, or if you are developing a new machine, you compare it with the existing machines. In the in this in these papers, they have used a EMTS, electromagnetic tracking sensor system. But first they did the static validation, where they designed objects with known angles, then placed the sensors on top of it, and then measured the pitch, yaw, roll of all of these configurations. So, in most cases, the configurations resulted in the known values were reported by the machine. In certain cases, there were errors, but more or less the system was robust. For dynamic validation, they have compared all the measurements to a EMTS sensor, electromagnetic tracking system. So the EMTS, so this is their system, and this is the normal standard sensor that was previously used. So whatever values they get should ideally, because this is kind of a gold standard, should ideally lie similar to the EMTS sensor values. At very low, so in these case the frequency is low. At very low frequencies, the measurements from the paper's IMU system and the EMTS sensor were the same. There were some differences, if you can see here, very minute differences in these portions. However, these were kind of minute in the grand scale of things. However, at very high degrees, high frequencies, the measurements diverted from the sensor, from the standard sensor measurements. Okay. So they needed to modify it slightly to account for very high frequencies. Okay. So to uh, so this was the initial system where every chip was pasted onto the skin, and then it was individually connected to a multiplexer. Then the multiplexer will forward the results into the system. So there were 16 such chips, and each of the chips takes 2 milliseconds to compute the coordinates. So it will take approximately 32 milliseconds to get the results to the system. However, uh, at very high frequencies, there was the problem that the measurements were not the same as the standard sensor. This problem also arises because of aliasing, whatever you want to call it. So what it essentially means is that there is something known as Nyquist criterion, wherein you whatever sampling you do uh, in whatever condition, your sampling at the highest frequency should be done at least twice. Okay, so if your sampling is done at least twice at the highest frequency, then then the system qualifies for Nyquist criterion. If the system does not qualify for Nyquist criterion, falls into the problem of aliasing, where the information is generated at a very high frequency, but the sampling is not done at that frequency. Because of this, you lose out on some data. Okay. Okay. um So the EMTS tracking system is known as polyhemus, and VNO is the tracking system that they have developed. And in this kind of a prototype, the initial prototype, the measurements were same, but very minute changes might be present, in which polyhemus was kind of better suited for those measurements than BNO. Then they further fine-tuned the system. So they introduced, uh, if you remember, there were master and slave fingers. Similar to that, in the similar lines, they have introduced slave microcontrollers and master microcontroller. So uh, there are still 16 sensors, 16 IMU sensors. It's just that for the middle finger has the master is directly connected towards the master microcontroller, whereas each of the other digits are connected to slave microcontrollers. From so these sensors will sense the information, input it into the slave microcontroller, then the slave microcontroller uh, uh, inter- will relay the information to the master microcontroller, which will finally uh, give the information at the system. So this kind of reduced the problem of aliasing. So now they were able to sample the maximum frequency that they could detect was 100 hertz. Earlier it was 30 hertz. Okay, so this is essentially uh, the diagram for that. So this finger is directly connected to the master, whereas these are all connected to slaves. These slaves finally connect to the master controller, master microcontroller, which will then use Wi-Fi to transmit all the information. Okay. And then they further experimentally validated the uh, data that they saw. uh, they further experimentally validated their setup using various Bharatanatyam postures, some of grasping movements where you hold a pen or you hold a ball, etc. And the way the fingers are arranged in that kind of a scenario was, uh, they essentially try to visualize it using so HKMS is their system, the new system, and EMTS is the polyhemus, the electronic tracking system. And they saw that in most of the cases, the postures that the hands were making was very well visualized by the HKMS system. Okay. Further, they also validated it for various ranges, and they saw that the ranges for the EMTS and HKMS system were more or less the same. So, if not better, the new system was able to adapt to the current uh, standards of uh, measurements. Okay. Now coming to gait analysis. So, for gait analysis, the before we go into gait analysis, first let's look at stability. So, essentially, stability is the criterion for in which if the overall the criteria for stability is that the center of mass is over the area spanned by the feet. So if this is the area spanned by the feet, the center of mass can be somewhere around here. It shouldn't lie somewhere here. In that condition, if the center of mass lies somewhere outside of this area, it is known to be instability. So, while uh, s- in upright standing, the right foot causes a negative torque. Sorry, in this case, right foot causes a positive torque, and this foot causes a negative torque, and the cancel. In cases where there is a shift, both of the torques will be in the same direction, either in this or either in this direction, depending on which side the uh, person is shifting. In those cases, there will be a magnitude of the torque. Okay. Therefore, these since the torques are not able to balance, there will be an instability. When the center of mass is to the left of the foot area, somewhere here, both torques are negative. When it is to the right, both torques are positive. Okay. Now, what gives stability to the system? It's the ligaments that hold the bones in the in its place. Just a sec. So we saw in the previous in very early classes about the ligaments that hold the about the ligaments that hold the bones in place. Uh, in case of the knee, there are four major ligaments that stabilize: medial collateral ligament here, the lateral collateral ligament, the anterior cruciate ligament, and the posterior cruciate ligament. So cruciate means crossover, collateral means on the same side. Okay, and this the knee is further stabilized also by oblique ligaments and patella. But these are the uh, four major ligaments that stabilize the knee: medial collateral ligament, lateral collateral ligament, posterior cruciate ligament, and the anterior cruciate ligament. So, um, if a body is stable, if there is overall stability, that implies that every joint is stable. At every in every local area, the joints are stable. So if a body is if somebody is standing stably, that implies their knee, their back, their ankles all are stable. And all, in all in all of the conditions, the center of mass will lie inside this area. Okay, so if in case if in case the a person is just standing without any other mass uh, that they are lifting, then the person center of mass will be somewhere around here. Whereas in cases where the person is holding on to some heavy object, where in those conditions the center of mass shifts to the outside of the body, and the person needs to compensate for the extra mass. This compensation, if long term, can lead to muscle strain, back pain, overuse of muscles. You might sprain or break something if the weight is too much. Okay, but in a normal stable scenario where the person is not lifting any weight, then the center of mass, and standing upright, then the center of mass will be somewhere around here. Okay, coming to ground reaction forces. So uh, essentially, Newton's law, every action has equal and opposite reaction. Whatever Whenever you are standing at any position, you have a weight, and this weight leads to a ground reaction force, which will be in this direction. Okay, so if a person weighs around 70 kgs, they will generate uh, their weight will be around 700 newtons. The force that uh, they will have is around 700 newtons, and this weight is supported by both the feet. So each and on an average, the cross sectional area of both feet, if you add both of them, is around 350 centimeters square. However, only the ball of the ankle and near the heel and the ball of the foot only touch the bottom. So the area that actually is in contact with the ground is less than 350 centimeters square on an average. So in if you do the computations, you find that the pressure on the feet when a person is just standing upright is around 10 newton per centimeter square. These forces change while walking, and it can peak at around 60 newtons per centimeter square. The forces that um, the ground the ground reaction force can be described using a butterfly diagram, wherein the each of the line is essentially one force in that unit length, unit area. Okay, coming to gate cycle, which is the time interval between two successive occurrences of any one of the repetitive events of walking. Now, what does repetitive events of walking mean? These are all of the uh, events that one would see if someone is observing someone walking. There is the heel strike, there is the mid stance, where heel strike when the front foot just touches the button, mid stance where the back foot is about to lift off, the front foot is flat, toe off, back foot has lifted off, and then the swing in which this foot comes to the front. This is swing. Then comes the next heel strike when the next foot will come to the front. So, on an average, the time between initial contact of one foot and the next contact of the same foot is considered to be one gait cycle. It can also be between one mid stance of one foot to the next mid stance of the other foot. It can also be one toe of one foot to the next toe uh, to the other foot of the same foot. However, you need to you need to have all the events lined up, or there should be one of each event for each foot occurring in one gait cycle. So both of the legs go through a combination of stance phase and swing phase. We'll come to that, and depending on it varies from person to person. If it's a if one might consider heel strike as the first contact, and the next contact as to be one gait cycle, they might consider mid stance as their uh, initial contact. It might vary. Okay, this has, I don't know why this isn't there. Anyways, so there are two phases: stance phase and swing phase. Stance phase and swing phase. So the swing phase is essentially this portion, whereas the other portions are the stance phase, where from heel strike to toe off. From toe off to heel strike is the next one. So, for the stance phase, the first step is foot flat or the loading phase, the mid stance phase, the terminal stance phase, and the pre swing phase just before toe off. For the swing phase, the initial there is initial swing which is encapsulated in this mid swing also encapsulated in this, and there is terminal swing encapsulated by the heat strip. So if you were to study the gait cycle of a normal person versus someone who has some pathology, say arthritis, you'll get to know that what are the differences between both of these uh, gates, and you can further your analysis from there. If you are to look at what times are present in different stages of walking, so essentially both of the legs follow the same series of event, but they are displaced by half a cycle. So there is this portion and this portion which is not there, in which there is no overlap. But other than, and these portion are known as double support phases, where both of the feet where there is contact with the ground. In other scenarios, it might be such that the one of the feet is always off ground. If there is no double support, then it does not quantify as walking. It quantifies as running or jumping or some other event, but it's definitely not walking. For walking, the double support is essential. Okay. Uh, so between um two consecutive double supports, there is going to be one single support wherein one feet is in contact with the uh, ground. Okay, the stance phase takes about 60 to 65% of the gait cycle. Swing phase takes another 35 to 40%, and double support is around 10%. And this changes with the speed, changes with the height of the person, which the speed obviously changes with the height of the person, the dimensions of their leg, and if there is no double support, there is running. It's called as running. Okay. And some of the other terms that one would encounter while looking at gait is stride length, which is the distance between, it's essentially this distance. It's distance between two successive placements of the same foot. Stride, another term that you would encounter is step length, which is distance moved by one foot in front of the other. So either this distance or this distance. Okay, this, there might be different step lengths. One of the legs might be smaller than the other, or it can be because of some pathological problems. There can be an injury because of which the gait length is not the step length is not the same. But the right step length and the left step length, if you sum them, you get the stride length. No, stride length is right step length plus. right step length plus left step length. Okay. Uh, why is it a problem? If there are different step lengths, it usually means that there is some problem with the single support on the other side, because of which you have a shorter step length. Yeah, this and walking base is the side to side distance. This, how much is the gap between both the feet? If they were uh, placed on a path and footsteps were marked, how much is the average gap between these two, the left and the right foot? Okay. The okay. Another measure is cadence, which is the number of steps in a given time. So it's essentially a measure of how many half cycles you go through. Instead of a cadence, a more standard unit is cycle time, which is 120 by cadence. And you can also compute speed by multiplying stride length, by dividing stride length with the cycle time, or essentially multiplying stride length into cadence dividing by, you can't see it here probably, stride length into cadence divided by 120. Okay, so these are all the measures that can be used. Okay. If are there any doubts? Otherwise, I can discuss the questions. Okay. Let me just share a different screen. Okay. So, uh, I'll discuss some of the old questions. Let me know if you have any doubts after that. Okay, coming to the first question. The dip joint has 2 degrees of freedom, true or false? Remember, dip joint can only move in one direction. Like, it can only flex and hyperextend, flex extend, and maybe to some extent hyperextend, but it can't move in the uh, other axis. So pause. In the adjacent figure, sorry, one sec. Okay, but I, okay. In the adjacent figure, qrist dash qprox dash uh, qmid, sorry, qrist, qprox, qmid, and qdist, all of the sensors indicate quaternion values obtained from the sensor placed on the wrist proximal segment, middle segment, and distal segment if of the finger respectively. Which of the following operations is used to in order to obtain the relative quaternion of the dip joint? So, if you want the dip joint, you essentially, if you want the dip joint, you need to multiply the conjugate of q mid with q dist. So, and then you will get the relative angle. If you want the sum of the angles, you can multiply q mid by itself with q dist. That will give you the sum. If you want relative, you need to conjugate this one. Okay, remember that. The inertial measure units IMUs used in hand kinematics measurement system HMKs is IMU 20, LSM 60, S3, Pearls 40 IMU, BNO 055. Answer is BNO 055. Correct. Select the correct statements. HKMS was experimentally validated using a typing task. Different hand postures and object grasp were used for experimental validation in HKMS. The HKMS was validated by static and dynamic calibration against highly precise electromagnetic tracking sensors, or a data glove was used to calibrate the HKMS. The answers are different hand postures and object grasp were used for experimental validation, and the system was validated by both static, where they had angles specific, had more models of specific angles which are used for static calibration. They knew what the measures were before making the measurements. It was also calibrated dynamically by comparing it with the EMT, the electromagnetic tracking sensor system. Okay. How many microcontrollers are used in HKMS? 1, 4, 5, and 6. No, the correct answer is 5. So there were 4 slave microcontrollers and there was one master microcontroller. Correct? So answer is 5. Select all the uh, statements, all true statements in regard to full hand kinematics measurement system designed using IMUs. The master and slave arrangement was required to achieve up to data update rate of 100 Hz. Uh, the BNO 055 was programmed to provide output in form of quaternions. The IMU based HKMS system is accurate than the optical trackers and the electromagnetic tracking sensors. The HKMS device used just 12 sensors to compute the kinematics of the full hand. Answers are A and B. We didn't really talk about the comparison with optical trackers and the electromagnetic tracking sensors. It was just used to as a standard against which the system was evaluated, and they use 16 sensors to compute the kinematics, not 12. A dash is the time interval between two successive occurrences of any one of the repetitive events of walking. Stride, swing phase, pace, gait cycle. Correct, gait cycle. Which of the following are considered when analyzing stability in gait? Center of mass over the feet, torque generated by each foot, knee ligament strength, cadence. You want to hazard a guess? You also look at knee ligament strength. If there is a breakdown in the strength, that implies that there is no stability. If you remember, the one of the points was that there is uh, there needs to be local stability for there to be overall stability in a human's body. Okay, so the answers are center of mass over feet, to torque generated by each foot, which should cancel out each other, and knee ligament strength. The dash diagram is a representative of ground reaction force or GRF vectors at regular intervals of a walking cycle. When, free body, butterfly, or network. Correct. Butterfly. If the pressure on the feet during standing is 10 Newton per centimeter square, the peak forces during walking can reach up to 10, 15, 30, 60 Newton per centimeter square. The answer is 30. Answer is 60, sorry, not 30. They can reach up to 60 depending on the stride, on the speed at which the person is walking. Okay, match the terms with the correct definitions. Heel strike. Heel strike is essentially for the for this particular uh, presentation. Heel strike. They have defined heel strike as the beginning of the gait cycle. Toe off when the foot leaves the ground. Swing phase. Correct. The answer is C. Swing phase is when the leg is in the air, and mid stance is when the body weight is directly over the stance tip. So answer is C. The stride length is the distance between two consecutive placements of the same foot. True or false? False. Sorry, this was supposed to be false. No, this is true. It's not false. The stride length is the distance between two consecutive. If you were to place your right foot, can I draw stuff here? Anyways, if you were to place your right foot here, left foot here, then again your right foot here, this complete distance will be your stride length. to 2. Which ligament is not part of the knee stabilization? Medial collateral ligament, lateral collateral ligament, posterior cruciate ligament, ulnar collateral ligament. Correct. D. Ulnar collateral ligament. It's present in the ulnus, not in the knee. What does the swing phase signify in the gait cycle? Foot is flat on the ground, leg moves forward in the air, heel touches the ground, foot leaves the ground. Correct. The answer is B, leg moves forward in the air. Which phases are part of the stance phase in the gait cycle? Foot flat, toe off, terminal stance, initial swing. Foot flat, toe off, and terminals and initial swing are the answers. Terminal stance goes into the stance swing phase. Okay. Are there any questions? Okay. I'll hang around for a bit if there are any questions. Otherwise, this is the end of the session. Thank you for attending.